A friend once asked me, "Do you prefer math or art?" I gave him a sort of disapproving look. I can't really blame him though. You see, to most people, art and math are two completely different fields, two forces independent of each other. To most, an artist is a free spirit, a creative mind with a passionate soul. Meanwhile, a mathematician is strict and tedious, eventually becoming a recluse in his obsession over his boring numbers. While I can't say anything about the first description, the second one can't be further from the truth. To return to the earlier scenario, I told him that the answer was art. He seemed confused, as he thought that I was a math person. To clear up his confusion, I told him, math is art. Is literature beautiful? Most people would say yes, as would I. The fact that we can interface our thoughts and emotions through sounds is amazing. Then how can one think that math is not beautiful? For what is math but the language of the universe? People often miss the splendid secrets hidden in equations that model our world. When they are viewed as more than just confounded jumbles of Greek letters and numbers, they can be appreciated for what they really are, an emulation of the magnificence that is nature. Take, for example, the second law of thermodynamics, which states that the disorder of the universe will always increase over time. When written in the form of an equation, it looks like this. Yes, that's it. The S is the symbol for entropy, or disorder, and the D in front of it means rate. In other words, the rate of change of entropy is always positive. Things get more disorderly over time. It took but four symbols to convey this complex idea in the form of numbers. Other equations, however, are more than just four symbols. For example, information theory. This beast of an equation gives the amount of information in a given message. No, not the amount of words or characters in the message, the amount of information in the message. Pure, raw, unadulterated information. Not yet convinced of the elegance of the equation? Take a look at chaos theory. This wonderful little thing describes any process as it becomes more chaotic over time. Anything. A classic example that can be described is the butterfly effect. A butterfly's wings on one end of the world causes storms on the other end. What is the common theme amongst these equations? Abstract ideas. Disorder, information, chaos. These are things that we can barely visualize qualitatively. Yet they are perfectly described quantitatively through numbers. Just as we use language as an interface to communicate emotions, the universe uses equations as an interface to communicate these complex ideas. Equations not really your thing? Don't worry, math shows up in other ways too. Mathematical patterns are the driving force behind the attractiveness and appeal of nature. For example, the Fibonacci series and its implications. Here's the series. Each term, save for the first two, is generated by adding the previous two terms. Now, if you were to make squares with side lengths of each of the numbers, arrange them in this particular orientation, and draw an arc that connects the corners of the squares, you get the Fibonacci spiral. The rectangle is important too. I'll come back to that later. Anyway, this spiral is amazing. It shows up all over nature. From seashells to pine cones, from hurricanes to galaxy arms. The Fibonacci spiral is everywhere. This is not because there is some fine print that the universe must follow, but because this arrangement pattern is so naturally efficient that many aspects of nature decide that they just want to behave that way. Seem too simple to be nature? That's because it is. Nature is more than just spiral arrangements. What about complex, disorganized structures, such as DNA, blood vessels, or trees? As it turns out, thinking of these as unorganized would be very wrong. You see, these naturally forming structures contain what are called fractals. A fractal is a structure that is made of itself. That is, it is self-identical. To illustrate this concept, here's a simple example. Take this line segment. Now, make two more line segments that branch off of the first, each half of the size of the original. Then, make two more off the ends of each of the two branches. Then, well, you get the picture. This ends up forming what is known as a fractal tree. In this fractal, the self-identity lies in the fact that each branch forms a tree, and each branch of a branch forms another tree, and etc. This pattern shows up all over nature. Leaves seem to be made up of smaller leaves. Rivers split to form smaller and smaller rivers, and bolts of lightning branch out to form more bolts. Humans have noticed these patterns, both fractals and the Fibonacci series, for centuries and have harnessed their innate beauty to make amazing works of art. Remember that rectangle I put aside? Well, if you divide the length of the long end by the length of the short end, you get approximately 1.61803. This is known as the golden ratio, symbolized by the Greek letter phi. The ratio was used to make the likes of the Parthenon, Venus de Milo, and the Mona Lisa. Meanwhile, fractals can be seen in the Great Wave of Kanagawa and Egyptian and Indian architecture. To demonstrate how simple it is to make fractal art, here's a simple program I made that draws circles. Just as a fractal is made up of itself, this program executes itself, exactly 20 times. Here's the result when it is executed. How amazing is it that all it takes to make this is an understanding of mathematical patterns? Mathematicians realize the immense beauty hidden in math. Just as an artist reveres art, a mathematician worships math. In fact, the two are so indistinguishable that I'd like to pose a challenge. Here are two quotes, one from a mathematician and one from an artist. Guess which one is which? Did you guess? You were probably wrong. They're both from mathematicians. To the followers of each, mathematics is indistinguishable from art. Just as artists become fanatics of their craft, mathematicians do too. Take, for example, Fermat's last theorem, posed circa 1630 by Pierre de Fermat. It theorized that for any n greater than 2, x to the n plus y to the n equals z to the n had no whole solutions. Fermat wrote in his book that he was reading that he had a marvelous proof for this, and then he died. After this annotation was discovered, mathematicians threw themselves into finding the proof. After 3 centuries, the problem was finally solved by Andrew Wiles in 1993. It was his childhood dream to solve it, and he did. And then there's the Riemann hypothesis. Posed in 1859 by Bernard Riemann, the hypothesis says that for the function zeta of s, known as the Riemann zeta function, equals 1 over 1 to the s, plus 1 over 2 to the s, plus 1 over 3 to the s, etc., zeta will only equal 0 when s is in the form of 1/2 plus xi for any x. I know, it's a lot to swallow. No one has proved it yet, but since many established fields of math rely on the hypothesis being true, whether or not it is true is a million-dollar question. Literally, anyone who can prove it, or disprove it, will be awarded $1 million from the Clay Mathematical Institute. There's been a huge frenzy over the last 100 plus years to solve it. Not for the money, but for the love of numbers. This is the sort of passion that is in all mathematicians. They all love and find solace in numbers. They recognize the coherent ubiquity of equations and believe that, by learning about numbers, they are uncovering the amazing secrets of the universe itself. In that sense, it is not necessary to have a deep mathematical understanding to appreciate the beauty of math. All it takes is perspective.